the lights, the power issue. So we'll be picking from where we left last time. So actually, I may need to share those particular notes. Okay. I hope that screen is visible. So this is what we were covering last, previous online session, and I think we go to the point where we were looking at the main building blocks of an FPGA. We talked about the CLB, configurable logic block. There was also the BRAM, the block RAM, and we were listing what this block RAM can be used to do. One, we said transfer data between multiple clock domains by using the lot of FIFOs, also to transfer data between an FPGA target and a host processor. So I think we can pick from here and just finalize on this before we now move to the next part, which is, how do we program or how do we configure an FPGA? So the block RAM can also be used to transfer data. Not just between an FPGA and a host processor, but it can also be used to transfer between the two FPGAs. And finally, we can see that a block RAM can be used to store large data sets on an FPGA. And this is more efficient as compared to using RAM built from a lookup table. So this block RAM can be used to store large data sets on an FPGA target more efficiently. Than RAM built from lookup tables. So then the other building blocks, I think, from the previous presentation, where we had, we are trying to zoom in into the core of an FPGA fabric. we were able to see these building blocks. So, in the interest of time, we'll not really get into the rest, just to state them, and in your own time, you can possibly go and read more about them. So, what we saw, we had the clock management tiles. Output banks. We also had the DSPs. Yeah, so these are the main building blocks, and I think we want to stop there, and now we can get to how do we actually program. Uh, how do we actually program an FPGA, or in other words, how do we configure it? So that is our topic for the day. Just a second. Yes, so when we come to FPGA programming, we talk of the hardware description languages as opposed to to the software programming languages that we are all familiar with. Um, so we have two main uh, HDLs, and these are we have Verilog, and we also have the VHDL that is in full. It is the very high speed. Very high speed integrated circuit HDL, which is commonly referred to as VHDL. So these are the main hardware description languages that you'll find widely being used. We have others like System Verilog, but for our purpose and for our session, we will concentrate on this. But even at the same time, we cannot cover the two languages, of course, given the short time that we have. So we will be covering. Previously, I've done very long, but for our sessions, maybe today and 1 hour more, we will cover the VHDL. So the two of them, whichever one you use, you should be able to achieve more or less, the same kind of functionality. But of course, there are different languages, different syntax. So we'll be covering the VHDL hardware description language. And what we'll be doing really is an overview of this and do some examples. And I think that will be sufficient enough, because we cannot cover everything about VHDL in 2 hours or in 3 hours, but we should be able to get somewhere. But nonetheless, these languages are not really as in-depth or as, I would say, as complex as the other programming languages, where you have to, there are very different things you can do and syntax and so forth. But for this one, it's simply hardware programming, and therefore it's really not as complex as software programming. So VHDL, the code structure of VHDL it consists of 3 parts. Consists of 3 parts. One is the library part, and as I said, we'll just be giving an overview. And for this library part, just as the name suggests, if you compare this to the software programming, if, for example, you're working with C, you have those header files that you may need to include. So include some H files and so forth, which contain the various libraries that you may need to use in your main code. So the same concept here. So we have some libraries that the VHDL, your circuit description will need to make use of, and they are included in the library. And there are 3 types of libraries available for VHDL designs. Here we have the library work, and this is inbuilt. It's inbuilt within the syntax of the VHDL, so you don't need to do anything, to include it in your project. It's implicit, so it's inbuilt or implicit. You can read further on what it does and all that. We will not be able to cover that today. But then we have the standard library. Same thing. This is it is inbuilt and implicit. So you also don't need to actively capture it in your hardware description language code that you will write, your HDL code that you will write. Then the other library is the library IEEE, and this is now what you will actively include in your code, because it is not built in. So it's not built in, and must be. So what does that library IEEE do? Now the standard library is the STD. This one contains definitions. It contains definitions for standard data types. For example, definitions for a Boolean, bits, integer, and so forth. So Boolean, integers, bits, and so forth. Just like in C language, you have the various data types. For example, we have the signed integer, unsigned integer. We have long, double, Boolean, and so forth. The C language and any other software programming that I would use in C to make some parallels with this. You'll find those kind of data types. So the same thing with this HDL, we have similar data types. The Boolean, integer, bit vector, and so forth, declared within the library standard, which is inbuilt or implicit in the VHDL. Now, the IEEE library, now you have to library, it enhances some of these data types described find in the standard library. So this library, we can make a few notes that this is the storage place, for 9 value logic or data type. Called and the standard logic. So this, as you may find out as you read more on this, you'll find that what is inbuilt, the library standard, we have seen it declares some data types, including the bit. So a bit is it's a two value data type. So it can either be a 0 or a 1. But you realize when you come to hardware design, you'll need more than a 0 or a 1, including things like high impedance. How do you program, or how do you indicate high impedance if you only have a low and a high, a 0 and a 1? So those are some of the challenges this library helps to solve. That is the library IEEE, by including a 9-value data type called the standard logic. And now this standard logic is preferred over the bit data type declared in the library standard, because it offers more options, nine possible values, as opposed to just 2 values declared in the bit data type. So we can note that the standard logic is declared is preferable over the bit data type as it allows more options, e.g., we have talked of high impedance. So instead of just having a 0 and a 1, we also have that state, a high impedance state. We also have the don't care state or the don't care specification. You encountered this, I believe, in digital electronics. We're doing the kind of maps. I think there was something you're referring to as they don't care. So these are now various values that the standard logic data type can take. So hence the need to have this in your VHDL design, as it allows you to have those particular declarations. So a library, the library part, it has two parts or two so it has two parts. One is the library clause, and I use clause. So the syntax of the syntax, I need to use a different color, maybe that one will work. So the syntax for this is you have the keyword. Okay, I think I'll have to use this. You have the keyword, the library, and then the library clause. In this case, it is the IEEE clause that we are including, and then we have the use clause. So we have to include some packages contained in the IEEE library, and generally, just as a standard, the package that will be including is the standard, the IEEE standard logic. This is the syntax, and you want to include everything that is contained in that package. So if you have been following this in your VHDL code, this is generally everything you have to do as far as the library part is concerned. You just have to do this. Why? Because the other two libraries, work and standard, are implicit. You don't have to explicitly include or declare them. So as far as the code structure of VHDL is concerned, the library part, you just need to have these two lines, and this is kind of a boilerplate. It's standard. So whatever design you're doing, you just start by typing that, and you'll have your library part covered. So so the other part of the VHDL code, so we have covered one. In fact, there are only three. So we are almost finishing learning VHDL because we only have two left. So the other part of VHDL code structure is the entity. Number two, we have the entity declaration. the entity declaration, and this is it's kind of a black box, or yes, a black box of what the design or the circuit that you are trying to build. So in this case, you only declare the inputs and the outputs. So let's say your design or your circuit has 4 inputs, A, B, C, D, and an output F. So essentially, you'll not be getting to the details of the circuit, but saying I have a certain circuit here, a black box. Its inputs are 4, A, B, C, D. Its output is 1, F. And that's it. You're done with the entity declaration. So this um, can be thought of as a block, a description, a block description that is a black box um, of the circuit, that you are designing. So you only need to declare the inputs and the outputs. So this is a list with specifications of all input output ports of the circuit that are designing, or the circuit under design. So the syntax, so maybe it's going to indicate that this, what is the syntax for library. So the syntax for entity declaration, the keyword is recognized by VHDL as being part of the VHDL language. So, for example, in C, anybody that can give us any keyword in C language, C programming language. And I apologize for the background noise. I believe it might be something that you can hear because of the machine, but I hope I'm clear enough. In an example of a keyword in C, yes, somebody has typed in there int, that is for integer. So if you type int in C language, it will be highlighted as being part of the C language syntax. So the same thing with this. So if you type library, so when it comes to entity declaration, the keyword is entity, and maybe something we should have noted even before we began much of this. VHDL is it is case insensitive. So you can use capital letters or small letters. So for example, if I was to type this entity either in lowercase letters or in uppercase letters, it will still be recognized as a VHDL uh, keyword, as opposed to, of course, for example, in C programming, if Mark Ngugi, if you type this int in a capital in C, will it be recognized or it will be regarded as something different? Can help us with that? Is C language case sensitive or case insensitive?
Case sensitive.
Yes, you need to be keen on that. So that means that even when you declare your own variables, if you declare your variables either in a certain uh, uppercase or lowercase, then you have to maintain that throughout the code. Otherwise, your variable is not declared, it's not recognized. So for VHDL, that's not the case. It is case insensitive. So whether you use capital or lowercase letters, still be recognized. So how do we do entity declaration? So this is what we're doing here, the entity, and using the keyword entity, and then you give it the name. So this is user defined, whatever name you want to give your entity or that circuit that you are building, that's what you put there. And then, so VHDL is also more verbose. It uses a lot of words as opposed to Verilog. So actually, Verilog is, if you are to draw parallels with the software programming, Verilog is the C language of HDL, because C is concise, not too wordy. That's the case with Verilog, but VHDL is a bit wordy, and something like Python. So if you are to compare Python and C programming languages, you'll find C is quite brief in how it declares things and so forth, as opposed to Python. So VHDL I would regard it as now maybe the Python. I don't know of this HDL part of the world. So entity name, then is, then port. So remember, we have said we are the entity just gives us the inputs and outputs, doesn't tell us anything about the actual design that you are building. So you have the ports. Port is also another what do you call it, keyword of VHDL. Then you have now your port name, user defined. That is user defined. We have the signal mode, and we will get to understand what is this as we move along. And the signal type. So if you have more than one port, that is the input output. So all these will be having the same kind of declaration. So this will continue for as much as you have the ports or inputs outputs to declare, and then you will close this with that bracket and semicolon, and then our entity is still open, so we also end our entity. And this one, as I was saying, is quite verbose, so we also have to declare which entity are we actually ending, so we still have to, the entity name still has to be captured down there. So that is the syntax of of the entity declaration. So maybe to note, for purposes of your notes. So this is just a note. It's not part of the syntax. So the syntax actually ends here. So the port, and this, I've said this is capital, is case insensitive. So the port tells the compiler that we are defining inputs and outputs, and outputs to the block. And this block is, our circuit, which is a black box. We, will not be describing what is inside that block as of this stage. Then there is the port name, so that is user defined. But we have the signal mode and the signal type. So this is where now whatever signal mode or signal type you use is now contained in one of these libraries, either in the IEEE library, in the standard library, or in the work library. So what is the signal mode? So the signal mode this can be either in, so is it an input, is it an output, or it can be out. So these are VHDL keywords, in, out, and for this is used in cases of where the port is a truly unidirectional. That is, it is either input or output, but not both. Then we also have a signal mode of the type in, out, and this is for the case of bidirectional signals or signals. So for example, if you are designing something to do with some data transfer, for example, I squared C, you'll find your data line is bidirectional. So data can come in, data can come out, and therefore you'll use the keyword in, out for that. Then the signal mode can also be of the type buffer, and this is needed when an output signal must be read internally. Then the other part of the syntax in declaring entity and declaring our ports is the signal type. So this signal type can be, of different types, data types that either are in the standard library or in the IEEE library. So remember, this is like the integers, the long integers, short integers, the Boolean, the strings, and so forth in C language. So the same case here, your signal type, it can be of the type bit, which library declares or defines the data type bit? Which library? Somebody? Which library within a VHDL defines the data type bit? Just to see who is with us.
STD.
Sorry?
The STD library.
Yes, yeah, thanks, Sherry. Yes, it's the STD library or the standard library. So that signal type can be of very different types. It can be a bit, it can be a bit vector. It can be, or it can be an integer. It can be of the type standard logic. And now this is from the library IEEE. It can be of the type Boolean, and many other types that are declared within the VHDL libraries. So it can also be a standard logic, a vector, etc. So basically, that's with this information, you are able to have your entity declaration done. So we look at an example of the entity declaration. We look at an example. So remember, this is the third part of the second part of the VHDL code structure. The first was library. The second one is entity declaration, and so that means we are almost done with the VHDL language. So this consider a black box. For a design entity named my circuit. So those of course that is a user defined term or variable. So this is it's your black box. We don't know what this circuit contains, but we know, or you know, as the designer, that you have various inputs and maybe a single output. So you have A, B, C, D as your inputs and F as your output. So as far as the entity declaration is concerned, this is what it will declare: an entity by the name my circuit, and then ports A, B, C, D, F. And now for those ports, it will say what is the signal mode. Is the signal coming in or out, or is it bidirectional, and so forth? And what type of signal is it? Is it what is coming in or what is coming out? Is it a bit? Is it an integer? What is it? So and that's sufficient. So so now we want to declare our entity using VHDL. We have given our syntax up there. Can somebody tell us now, what do I start with? Now I'm typing the code. What do I type here for entity declaration? What do I start with? What do I type? Entity declaration, what was the syntax? What do we start with? Yes, somebody?
entity name.
Okay, thank you, Emmanuel. Yes, we start with the entity, the keyword entity, the name of that entity. So in our case, we have said we are calling our entity or our design my circuit, and then is now we can come down there and type port, but for legibility or for clarity, we can put it here, and then we have our opening and closing brackets. So we have something, so there we'll put some things there, and we'll close our entity by end. And once again, VHDL is verbose. We still have to type my circuit there. Yeah, so basically that's the skeleton of entity declaration. You should not miss that. But now inside here, we now put in our various inputs and outputs. So looking at this syntax, so you can see it's port name, colon, the signal mode, the signal type. So port name, user given, is we have A, B, C, D, F. Those are our port names. And the signal mode, is it in, is it out? So at least we can, or at least we know, because of course we are just, if you are to be given this, you will make an assumption that A, B, C, D are inputs and F are outputs. But it could be the other way, So, but because we are the designers, we are saying that A, B, C, D are inputs and F is our output. So we can choose to declare each of those ports individually. So we put A colon, the signal mode is input, signal type, we prefer to use the standard logic because that gives us a 9 value, a 9 value instead of, for example, using the bit, which will just give us 2 possible states or 2 possible values. So most of the time, these ports will take a signal type of standard logic. So we can choose to individually declare them. So we say A, signal mode in, signal type, standard logic. B, in, standard logic. C, in, standard logic, and so forth. Or we can kind of combine them such that we have A, we have one of our ports is A, we also have B, we also have C, we also have D, and all these are, so column, all these are of the signal mode in, these are inputs, and they are of what, signal type. Thereof, we declare them as standard logic. Yeah. Declare them as standard logic, and then we have F. We have F, which is output. So this is of the signal mode out, and signal type still standard logic. And that's it. This is a complete VHDL code, and syntax-wise correct. We have declared our entity using these keywords: entity, my circuit is port, then the various ports, inputs and outputs. As I said, you can have these A, B, C, D in their own lines, complete with in standard logic, or you can combine them, and the compiler will know that A, B, C, and D, they are inputs, they are of the type standard logic. But for F, it is an output of type standard logic, and then you end your entity. So that is the syntax of the entity declaration, and that's a complete VHDL code. So our code structure library part, entity declaration is done. So we only have the third part. So I say the code structure of VHDL is divided into 3: library, and so for the library is the easiest. There's nothing really you have to do or to even remember. Well, you only need to remember these 2 lines, and all they will be consistent across all your designs. That is the default. Just like when you're given an exam, the first thing you write is your name and registration number. So this is the same thing. Library triple and this. So it doesn't matter whether you're doing whichever paper you're doing, those are constants that will write your name and registration number. So, well, maybe you don't write your name, but at least registration number. So the same thing here, the syntax for the library. For entity, it's also more or less the same. In fact, the only thing that you will change is the name you give to your entity and the name you give to your inputs and outputs. The rest will be more or less the same. So, so that shows us actually, this HDL language is not as difficult as we may have imagined. So the third part, number three. Yes, Shabaki. Yes, Shabaki.
Like I wanted to from the sample that given us something like the semicolon is after the end of the brackets instead of end my circuit. Like the example, if you could scroll up. And also I wanted to ask like if there is, because I'm seeing like and there's no semicolon after entity in my circuit, but in the one you're giving us there's a semicolon. So that's
okay.
like I quite wanted to ask.
Okay.
I don't know if you can.
I've got your question. Yes, let me see. Yeah, well, here we have put the colon, the semicolon, after this closing bracket, and here we have put it at the end of my circuit. Now, actually, we will do this, we'll actually compile some example, and that will highlight the various mistakes we may have done. So, this typing by hand, can introduce these errors, but the compiler will let us know where we have made a mistake. But I think the example we have done here is the correct one in terms of the syntax, because within this port declaration, the last line should not have a semicolon, because that semicolon kind of closes the whole entity, at the end my circuit entity. So the correct syntax really is this. The last line should not have a semicolon. That semicolon should be 1, and it should come here. So I think, so for this one, we didn't have, we just indicated that the port names and all this can continue. So actually, I think both are correct, but we'll see when we compile, because the last line, just before this, I don't know whether you can see my cursor, just before this closing bracket, we should not have a semicolon, just like here. you should not have a semicolon before this closing bracket. The semicolon comes after. Now that semicolon, I think both are correct. It can come at the end of this end my circuit or the end of this bracket, but I think we'll verify that when we actually do the compiling. But yeah, I think we can take this example as the standard entity declaration. The key thing and the takeaway is, as far as the syntax is concerned, your last line should not have a semicolon. Remember, this A, B, C, D could be on the individual lines, and all those lines would have the semicolons. But the last one shouldn't have a semicolon, or just before the closing bracket here, there should be no semicolon. Now that semicolon comes after we have ended that entity declaration. And I'm saying that semicolon now can come here or after this bracket, that will verify that in the compilation. I hope that is what you are asking, Shabaki.
Yes.
Okay, so the next and the last part is the architecture declaration. So from the entity, we come to the architecture. Declaration. So, and this is the last part of VHDL code. So if you know the library part, you know the entity declaration, the architecture declaration, then you should be able to write VHDL code without any challenge. So it's really not difficult. And as I said, it's not as complex as software programming. If you get the syntax right, the keywords right, then you should be able to come up with these designs quite easily. So, but you'll also realize up to now we have not really designed our actual circuit. We have done just some minor things. We have not really done any circuit design. And the actual circuit design now comes in the architecture declaration. Our entity, we considered our circuit as a black box. In the architecture, we define what is actually in that entity, what is in that black box that we declared in the entity part. So that is the role of the architecture declaration, that you now actually design or describe the circuit that is inside the black box that was defined or declared in the entity declaration. So actually everything as far as your actual circuit design is concerned is captured in this third part, the architecture declaration. So this is where all the magic takes place. And we can take a 5 minutes break, and we'll pick up from here. Okay, we can continue. And I see some two questions on the chat. Which signal mode is used to assign a high impedance? Signal mode. We only have three signal modes as per what I've expressed here: in, out, in, out. Yeah. So for high impedance, this is a value, that a particular signal can take. So the high impedance, just like high impedance is a value like 0 or 1, for low, or high, which is a 1, low is a 0, and then we have another state, high impedance Z. And we are saying that if we were to declare our signal type as a bit, then we cannot have a value of high impedance. A signal declared as of type bit can only give us low, that's a 0, or high, a 1. But if we want to incorporate other possible values of our signals, including the high impedance, then we have to declare that signal as of standard logic. And that's why we said that the standard logic is widely is the recommended signal type in most cases. So by default, you'll find that you'll be declaring your signals or your ports as standard logic, and as long as that is declared, then you can actually have a high impedance value. So with signal mode, I mean the high impedance can either be coming in as input, and therefore that can be the in signal mode. The high impedance could also be, being driven from your circuit. Your circuit can output either a 0, that's a low. It can output either a 1, that's a high, or you can even drive a high impedance. That's, you can put it to high impedance. So that is another state. So so the signal mode, I don't know whether I'm getting the question. So the signal mode can either be in or out. They can be bidirectional, but it has to be of the type standard logic for you to drive it to high impedance. I hope that makes sense, Davis, because I think you are mixing signal mode and signal type. Is Edward Davis, is that clear? Okay, then the other question was how would I read an out signal within an entity without using a buffer? Well, we said, for the signal modes, you can have in, you can have out, you can have in, out, and you can have buffer. And we said you declare your signal as of the signal mode buffer if you need to read it within the entity. You don't need to output it, as an output of the entity, but you want to use it within that entity itself. So you use a buffer, a signal mode that is needed when an output signal must be read internally. So your question is, how would I read an out signal within an entity without using a buffer? Are you talking of use? The buffer here is a signal mode. It's a signal mode. It's not a buffer in the sense of the NOT gate or something of that sort. This is just a keyword in VHDL a keyword buffer, just like in or out. It's not a particular component, just like the case in is not a particular component, out is not a particular component. So if you want to read your output signal internally, then you have to declare it as a buffer. But if you want to output it from the entity, you declare it as out. And maybe now the question maybe that might arise is that if you want to do both, you want to use the same signal internally, but you also want to have it externally. And my answer to that is, you use the out keyword, because actually I've not really had to use a buffer in any of my designs. They are basically either in or out, and I believe out should be sufficient for all these cases. I'm not really sure whether it's absolutely necessary to declare your output signal as buffer if you really need to read it internally. I think out is sufficient for both cases. So if your signal is being utilized externally as well as internally, I believe it should be sufficient to declare it as out. But because we learn how to do this VHDL programming, you can actually practice, or you can actually evaluate where you are using out and buffer keywords on your output signal and see whether it will make any noticeable difference. So I think that should answer those queries. So I will continue in the interest of time. So what we are looking at now is the architecture declaration, and this really is where your circuit is designed. So this describes the actual digital circuit. The actual digital circuit, and the actual digital circuit is actually now the component of this black box. So this is the contents. So it describes the contents of the black box, inputs of the black box declared. Declared within the the entity declaration. You can also note that it contains the intended circuits structural or behavioral. So what is the syntax for architecture declaration? So just like we had the keywords, for the library, we had the keyword library. For the entity, we had the keyword entity. For the architecture, we also have the keyword architecture. So you always start with those keywords. So what we are looking at now is the syntax, and the syntax for that, we start with the keyword architecture. We start with the keyword architecture. And then, just like we did with the entity declaration, we have to give a name to our architecture, just like we give a name to our entity. So architecture, you give it username, your whatever name you want to give. So we have architecture name, and now this architecture, it is of which entity? Because remember, now you are describing the contents of a black box that you declared in the entity. So you have to, as I said, this is highly verbose. So yeah, so architecture name, and this architecture, it is of this entity, the one we described here. So the entity name, you give the name of your entity, that whose architecture now you are describing. So architecture name of entity name. So these are user defined words or variables or names. And then is and now there are two parts to this architecture. One, there is what we call the declarative part. And we will describe what that is. We have the declarative part. And once you have done some declarations there, you'll begin your circuit definition. And once you are done, you'll end that architecture. So once again, we end our architecture. So we have to capture the name that we give to our architecture. So here is where we have your circuit. You are defining your circuit using your VHDL code. So this basically is the architecture syntax. This is the architecture syntax. As you can see, it's also very, very straightforward. So architecture name, it is of a particular entity. Then you have some declarative part. Then you begin your code and you end. And you have to end with the architecture name. That's it. So what is the declarative part? We'll see more in the examples, but we can just note that the declarative part this can contain the same items as the entity's declarative part, plus the component and configuration declarations. Now we are saying that you can contain the same items as the entity's declarative part, but when we look at our entity, we don't seem to indicate any declarative part. Yes, I left that intentionally, because rarely will you find or will you need to declare things in the entity. But if you needed to declare a few things, then you would have a declarative part just before you end my circuit. So after the ports, this closing and opening brackets, you have a declarative part and then end my circuit. But rarely will you have to really use that. So we can safely leave it as it is. For the architecture, you'll also rarely need to use the entities declarative items, but you will commonly use components and configuration declarations, and we'll see what those are as we progress, especially when we come to the various approaches utilized in architecture, in the architecture part, because up to now we have not really said how we do our circuit. We have just put code, in brackets here, and that is where our circuit is actually defined. So how do we design or define that circuit? So that is the next thing that we are looking at, which is basically under the architecture declaration, and that is VHDL design styles. So this is still under the architecture declaration. We have the VHDL design styles. And we will note that VHDL it has 3 design styles available for use in the architecture declaration. So which design styles are these? So one, we have the data flow. We have the data flow design style. We have the behavioral design style. And the structural design style. So what we are seeing is that, yes, this is the syntax for architecture declaration, but where we have indicated this code, this is where we actually design the circuit. We are seeing now there are 3 design styles that we can use in this architecture declaration. That is for this part of the code, where we have the code, the actual design of the circuit. We have 3 designs styles that we can use here. So maybe for purposes of your notes, we can indicate that this is where those design styles are applicable. That is the data flow. So this, whatever we do there, can have the data flow design style, or it can have the behavioral design style, or it can have a structural design style. And we shall look at what that means. And you also see that if we look at this, the data flow, behavioral, structural, then we'll have completed the architecture declaration, because the rest are, there is actually nothing else apart from this declarative part, which most of the time you'll find it coming into use when we are looking at the structural design style, or well, all the design styles, we'll put a few things in the declarative part, but the chunk of it is really this code part, where now we design the circuit in these different styles, whichever one we choose to use. And once we have reviewed this, then we'll have completed the architecture declaration, and in essence, we'll have now finished a full VHDL code structure from the library to the entity to the architecture declaration. Of course, this is reviewing as at a fast pace as we can. But if you spend a few more hours into this, you can actually do some proper circuits in VHDL, because it's not really complicated. Yeah. So very quickly, we'll review these three design styles. We'll not get into so much depth, just the basics. So what is data flow design style? So in the design style, we can use only the following in this design style. One, we can use the Boolean equations. So you can have your circuit described using Boolean equations, and now you implement that Boolean equation or equations in VHDL. So we can use the Boolean equations. This is the simple signal assignments. We can also use conditional signal assignments. Conditional signal assignments. Just a second. Okay, I can continue. Sorry for that. So we can also use in the data flow design style, we can use selected signal assignments. The selected signal assignments. So what this design style, it implies a corresponding gate level implementation. So the data flow description directly implies a, a corresponding gate level implementation. i.e., it implies how the hardware should be created. So in other words, for example, if you take a Boolean equation, it will show the various gates that you can use. Maybe there will be NOT gates, OR gates, AND gates, exclusive OR gates, and so forth. So from the Boolean equation, you actually write a VHDL code that essentially implements those particular gates. So it implies a corresponding gate level implementation, and we will do an example on this. And because of time, we'll not be able to cover all. For example, here we are saying we can use Boolean equations, conditional signal assignments, selected signal assignments. So for this case, we'll just look at one, probably the Boolean equations, and then you can go and read more on the other, the conditional and the selected signal assignments. Then the other design style that you can utilize in the architecture declaration part is the behavioral design style. So for under this, we can use the following. Still, we can use Boolean questions here. We can also use if statements as well as case statements. So just like in C programming, you have the if statements and the case statements. So we also have similar kind of things in VHDL. That is if statements and case statements. So when we talk of behavioral design style, this compared to the data flow design style, where we said that style implies a corresponding gate level implementation. The behavioral design style does not imply a particular gate level implementation, but it generally describes the behavior of that particular circuit, and but how you achieve that behavior is not is not directly implied. So it doesn't really tell you use this particular gate and this gate and this gate to achieve the results, but it tells them how the circuit should behave, and therefore can be implemented in probably different ways as opposed to the data flow design style, which kind of very directly implies what the gate level implementation to use. So for this, and some of these things will become clearer when we do some examples, and also as you do further readings on this. So here we can note that this is the most abstract style, in that it does not directly imply a particular gate level implementation. It does not imply a particular gate level implementation. You can also note that it creates the structure. It creates the structure for a circuit by inference. That is from deduction by reasoning from the general to the specifics. An example will do more clarity on that, as well as when you get to read more on this, become clearer. The other design style is the structural design style. This is the structural design style, and this more or less is a modular kind of design style, where you break your circuits into various components or sections, and you individually design those particular components or modules, and then you join them together. So it's a modular based design style. If you look at software programming, for example, if you're doing C or in any other, you're using any other language, you will find that most of the times you are not putting everything in your main code. You are not you're not writing code in your main application from A to Z. Maybe there are some areas, for example, if you're doing some embedded systems design, you have some display, LCD, you have some keypad, you have some sensors. You may find that for the keypad code, it is in its own .c file, maybe keypad.c file. If it's the LCD code, it is in its lcd.c file. If it's some sensors, they are also in there, some sensor.c file. Yeah. And you have written codes for that. So, you have mapped the keypads, for the LCD, you have the various commands and all that. You have programmed those in the respective C.C files. And then now in your main code, you will more or less be calling those particular functions that you have declared and defined in those other C files. So your main file, in fact, when in fact you'll find that in more, in more, will I say, experienced or expert level kind of programmers, you'll find their main application might actually be less than 10 lines of code, and you wonder what's happening. But most of the functions and the rest of the code is in the various other files, which are now being called into the main file, and the main code is just simply to glue everything together and to start the application. That's it. So the same concept here for structural design style. You break your circuit, because you can imagine the circuits can be very complex, and you don't want to put everything in a single file. Not only is it prone to errors, but it's also even actually difficult to do that. But if for each part you do its own VHDL code, and then you bring everything together using a top level file, it makes things much easier. So that is the concept behind the structural design. So we can I'm trying to see what we can capture, what I've said in so many words. So we can note that hardware blocks or components. So those, what I was referring to as .c files, as far as the C programming language is concerned, in VHDL, we would refer to those modules as components. So those individual parts that you have written VHDL code for, so that now you can bring them together into one main circuit, they are referred to as components. So it's analogous to the .c files in C programming. So hardware blocks or components are used. So that is the meaning, because if you're not in class and you just read the sentence, it will make you may not really understand what is hardware blocks or components are used. But this is essentially those modular designs that are now being referred to us as components. And then we also note that an entity is declared as a set of interconnected components. So in structural design style, for you to actually be able to break your circuit into various parts, you actually need to visually see the circuit. You if you are given a Boolean equation, you really can't do that. You can't do the structural design style until you actually translate that into a schematic or a circuit, and now you see which areas you can group together to form one component. Other areas, you subdivide your circuit into components. So for this, we need to use an annotated circuit. Circuit or schematic. It must be provided to use this design style. And then maybe the last thing I would want us to mention. So our analogy with the C programming language, we talked of the .c files, and then and of course in those .c files we have the various functions. And now in our main.c file, we kind of we say calling those functions, calling the functions that have been declared and defined elsewhere. Those could be in header files or in .c files. So in VHDL, the components that we have declared and defined in some other VHDL files, how do we call them into the main VHDL file? So instead of saying calling those functions, here we talk of instantiating those particular components. So we'll talk of instantiation, and this, as I've described, is analogous to calling functions that have been declared elsewhere. So in this case, of course, we're dealing with circuits and some components we have defined and described in a different VHDL file, but we now want to put everything together. So in our main VHDL file, we instantiate the various modules or components that we have declared elsewhere. So the installation, and that is the note that we are capturing here, the installation or placement, the installation or placement of the hardware blocks of components so we refer to that as instantiation. It's referred to as instantiation. And their interconnections as port mapping. So I think that is at least as far as the various design styles are concerned, that is a good summary or review. It will get, at least, for example, in the data flow and behavioral design style, we can do examples using either of whatever it is we have listed there, and we will also look at the structural design style, in examples. But here, this is a structural design style. It also, it's not very clear. So once we have subdivided our circuit into various components, and now we are individually developing VHDL code for that particular component, what do we use? Do we use a behavioral design style for each of those components, or do we use a data flow design style for each of those components? We can choose either. So just to finalize on this, so let's say this is our main circuit, right? This is our full circuit, and in this circuit we have determined that we can have the various parts which we are calling components. So we do VHDL code for each of these, and then we bring them together to form our main circuit. So this is our main circuit. This is our component A. This is our component B. This is our component C. And when we talk of component, it's not a component as you know it in electronics, where it's a single component, but this is actually a collection of various components and logic and so forth that we are calling a component. So in this component, we can actually decide to develop VHDL code for it. So the VHDL code for this, we can choose to use behavioral design style. For component B, we can decide to use data flow design style. For component C, we can decide to use data flow design style, and so forth. But we have subdivided them into individual components. We develop VHDL code for them independently, and then finally we call them from our main circuit file. And to do that, we instantiate the components in this main circuit file. So, and that is what is referred to as the structural design style. So you'll find, yes, it's structural design style, but you're actually making use of both behavioral and data flow design styles in the individual components that you are actually designing. So I think that should be clear enough that this is what is the subdivision, really, is what is referred to as the structural design style, that modular design. But individually, each of those components, you can actually develop VHDL code either using behavioral or data flow. I hope that is clear enough. So before we do any examples, because we will do them anyway, not now, but we also need to review a few syntax properties for VHDL, because we have talked of the structure, the code structure of VHDL: library, entity, architecture design, and the architecture declaration. Those are the three parts. And within architecture declaration, we have said we have, this is where we do the actual circuit design. And that actual circuit design can be achieved in three ways. using 3 design styles. 1, the behavioral design style. 2, the data flow design style. 3, the structural design style. So at least we are getting somewhere. But the VHDL, just like any other language, is not just about the structure, but we also have some other associated rules and syntax. So we'll spend the next few minutes to review what we can, and then we'll continue from there. So the first thing we want to review is VHDL. So we have VHDL, data objects, and data types. So we start with the data objects, and because of time, we really try to rush through this. All this is information that you can easily look up and get more from it. So we are advised to actually do that. But we can note that there are 4 classes of data objects. There are 4 classes of data objects in VHDL. 1, I need to use a block. So 1, we have signals. So we have been talking of signals. What exactly are signals? So this an object belonging to the signal class has a past history, of values. It has a current value, or it can have a current value, and also a set of possible future values that are to appear on the signal. Next thing we can note is that these future values that are set to appear on the signal, future values, can be assigned to a signal object using a signal assignment statement. As I've said, you review more on some of this, so we'll just highlight a few important notes. So the next thing on this is how do we actually declare a signal declaration? What is the syntax? And the syntax is as follows. So we have a keyword signal, that means it is part of the VHDL syntax, and then we give it a name. So this is user defined name, signal name, and then a column. We have a signal type. You remember the various data types that we talked about. could be a bit, could be a standard logic, but we said most of the times we'll be using a standard logic, especially if there are chances of it not taking the values 0 and 1 only, but it's susceptible to have some other values, then use standard logic. In other cases, if for sure it's just a 0 or 1, you can use the data type bit and so forth. So signal type, then you give the value of that, if it has some initial value that you need to give. So this is the syntax. This is the syntax of signal declaration. So very straightforward example. Let's say you have some signal. So the keyword signal, you give it a name. Maybe it's that signal is a clock signal, to give it that name. Then we have the colon. It is of what type? It is of what type? Maybe maybe if it's a clock signal, then it is, it's a pulse, low, high, low, high, low, high. So it can only take 0 or 1. So you can simply give it or declare it as of the signal type, a bit. So we can declare it as of the signal type, a bit. And if you want it to have an initial value, then you can proceed to initializing it as such. And so if you want it to have an initial value of 0, then you can initialize it as such. So that's an example of the signal declaration. And there are a few other things around signal declaration and signal, but for now we can proceed to the next key property, or property on the signals, that is signal assignment. Signal assignment. This signal assignment, this schedules a new value, to occur at some future time. It schedules a new value to occur at some future time. The current value value of the signal is never changed. At that point of assignment, you are scheduling a new value to occur at some future time, but whatever is currently on the signal is not changed at that instant, but at some point it will change now to the new value that is declared. So that means there is some aspect of also giving the time at which the new value will come into effect. But also you can assign, you can intend to have the new value appear as instantaneous as possible. So that means you don't indicate any time delay that new signal new value will appear. So for such cases, if no specific value of time, is specified, if no specific value of time is specified, okay, so it's taking out everything. So this one we see this never changed. Okay. Then if no specific value of time is specified, then the default value is infinitesimal. Okay. It is it's a very small value. So by default, the value will change after some delta time, infinitesimally small time. So this is the delta time. This is so the new value will be assigned to the signal after that delay, a delay of some delta delay. Then maybe lastly, we can note that signals are assigned. They are assigned so examples of signal assignment. Examples of signal assignments. So we have maybe a signal x1. So we have said we assign that. Okay, let me that will not be a keyword. So it is a user defined signal. So user defined name. So x1. We are now doing assignment. So in this case, we have said we will use the operator less or equal to. So that is the operator for signal assignment. So we are assigning a value of I'm trying to use different colors just to so we are assigning that value of 1, and we said we have to give some time when that change should come into effect. So in this case, we can declare it will come after 10 nanoseconds. etc. We can also maybe have another signal SR1, whatever that might be. We are also assigning it a value. Let's say a value of now this somewhere probably was declared as an integer, so we are assigning it a value of 5. So for x1, we can imagine it was declared, in our signal declaration as being of the type, signal type bit. So it can take either 0 or 1. SR1 means if it's taking up a value of 5, then at some point it was declared as an integer. So we can assign it a value of 5. Maybe that should come into effect after. So this after is a keyword in VHDL. So this can come in maybe after 5 nanoseconds. We're almost winding up our session, the next 1 minute. And then the other cases that you want it to kind of take effect as instantaneously as possible, and therefore we don't indicate at what point it takes into effect. So we want it to come to a value of 1, almost instantaneously. So we don't have any after. So what does that mean? So if so what how will this work? So let's say we have our just to show how this would look like. So we have an example of a timing diagram. So we have our, this is too close because we just need to indicate. So let's say this is our time 0, this is our time t plus 5, this is our time t plus 10, and this is our, actually not 0 because we don't know at what time we are starting, so this is at time t. So our value x1, it takes a value of either 0 or 1. So we have so this is x1 and take either a value of 0 or 1. So assuming that okay, we don't know what was the value of x1 before the 10 nanoseconds. So maybe, so in that case, it's at some high impedance, and that's why it is important that x1 is the type would be declared as a standard logic, so that before time t0, this is some high impedance value, until now after 10 nanoseconds, it takes now the value of 1. Yeah, so x1 becomes 1. What about SR1? So SR1, we have our SR1 here, SR1. So this is an integer. So before the 5 nanoseconds, at some high impedance, and then after those 5 nanoseconds, it will take a value of 5. So it will take a value of 5 onwards. What about x5? X5 is almost instantaneous. So it takes either a 0 or a 1. It takes either a 0 or a 1. But as we said, if there is no specific specific value of time specified, then the change will occur after an infinitesimally small value of time known as the delta time. So it will be in high impedance for a very small time before it actually picks up its new value of 1. So this is what we are referring to as the infinitesimally small value. So this is t plus delta, plus the delta time. So anyway, this depicts signal declaration, signal assignment. The key thing is the syntaxis of that, and the effect of, for example, this after 10 nanoseconds, after 5 nanoseconds, and in the case where no time is given. So we'll stop there for now. When we meet next, we'll review a few other data objects and data types, and then do some actual programming, compiling, executing, and we'll end there. So the next session of 2 hours, we should be able to finalize on that. So I don't know whether the class rep is back, but I will be away. I'll be traveling today, and I'll be away until next week on Wednesday. And I'm hoping that I will be able to have an online class on Monday from where I will be, but that is subject to confirmation. Once I get there and evaluate the situation, be able to see whether I can have an online class on Monday, so that we can finalize on this FPGA programming. So the class rep, I will communicate to you. We will be having a class on Monday online. For tomorrow,